Hey, good morning, guys. Hopefully yesterday made sense with our counting squares and trapezoid approximation. And today we're going to extend that a little bit. So we're going to call it kind of integration today. Basically the same thing with RAM, which actually means rectangular approximation methods. Now, this is something I guarantee you that you will have to do on the AP test in 3 different ways. So this is as well as the trapezoidal one from yesterday. However, let's get a little back thing we go as we know here. So what do we know? We know a definite integral. A definite integral is the area under a curve. Well, to be a little bit more specific on that, it's the area bounded between the curve and the x-axis, okay? So it's always going to be bounded beneath the curve, yet above the x-axis, okay? What else do we know about a definite integral? Well, definite integrals, they represent some quantity. That quantity could be distance or volume. It all depends on what the units are, and just some units we could get out of here. I mean, we could get volume, it doesn't matter. It could be gallons, okay? It could be anything. Could be miles like we got. Could be kilowatt hours. Could be inches cubed. It could be the type of units we get and the quantity that these definite integrals will end up representing is really kind of endless, okay? There's lots of different things that we can represent. And what we did is we found this by summing basically y times delta x every time we did this. Even when we found the area of our square, we took the base of the square, which represented our x, times the y, which was the height of our square, and we multiplied those, and then we summed all of those squares together. Or, with our trapezoids, we took our height of our trapezoid, which happened to be the horizontal distance, and then what happened was we ended up averaging our heights, which was base 1 and base 2. Okay, those end up getting average. That's why it's divided by 2, and that cuts it into a rectangle. Bottom line, to get that definite integral, we summed together all of those trapezoids that we drew underneath there, or we summed together all of those squares that we found the area of, okay? So in the end, a definite integral, please remember, is an area accumulator. That's what a definite integral is. It's an area accumulator. Now, we have done our area accumulating with two different methods. Okay? The 2 methods we've used so far. Well, we counted squares. Okay, counted squares. We did that yesterday on the truck problem. We did that yesterday on the football problem. And we also counted squares, on Ella Vader, Darth's daughter. Okay, trapezoids. Well, how did we do the trapezoids? Well, we only did the trapezoids on Ella Vader, okay, because we don't want to do everything, every different technique on every one. Well, today we're going to be looking at something new. Today we're going to be looking at a Riemann sum, okay? And to kind of give you a little backdrop, which I should have done up here, integration, we're going to be going from where we were, and what integration is going to do, it's going to move from counting squares, counting trapezoids, and it's going to move into this funky little symbol from A to B of f of x dx, where in the end, this is going to be my y times my x, and I'm going to sum all of my rectangles together from A to B, and that's what brings out what's called a Riemann sum. Okay, a Riemann sum is kind of new today. And what we will do, we will squeeze tiny rectangles under the curve. Now, granted, we're going to let n equal a different amount of rectangles numerous times throughout this lesson. And as we let n approach infinity, there becomes an infinite number of rectangles beneath the curve. That's why they get so skinny. And when I sum together all those rectangles, well, that gives me the sum of all those rectangles. That is what a Riemann sum is. Okay, it's new. And a Riemann sum is pretty much the basis. This is what this is, a to b of f of x dx. This is where, right here, this is where we will be in a little while, not today, but I find it more important that you understand what these symbols are doing more than just a process or an application of doing it, okay? So really try to focus on what all this stuff is doing. Now we're going to come to the next thing. What is a Riemann sum? Well, what is a Riemann sum? A Riemann sum is the sum of the areas of rectangles. Okay? And it could be 2 rectangles, it could be 10 rectangles, it could be 15 rectangles, it could be 100 rectangles, it could be 1,000, could be an infinite number of rectangles. That is what a Riemann sum is. Okay, there are some specific quantities that we must recognize and be able to represent. What are we talking about? Well, you should have a little line here to make a graph, and I'm just going to make a graph here. And you can make it however you want. And what we want to do is we want to find the area under f of x. So this is going to be my f of x curve. We want to find the area under f of x and the area under that curve and the x-axis on the interval from A to B. Well, that means I need an interval here. Now I'm going to say, here's my interval. I'm going to start here at A, and let's say I end up here at B. Okay? So I'm going to go from A to B. Well, how do we do this? Well, what's going to end up happening is we are going to divide from A to B into n subintervals. Okay? Now these could, they don't have to be, they could be equal in width. And for us, they will be equal in width. They don't have to be, if you look in your book. They do not have to be equal in width. However, we're going to make them all equal in width because it's going to make our calculations easier. And it's irrelevant in the end because as we let there be an infinite number of rectangles within an infinite number of subintervals between A and B, those widths become so skinny that you really can't see or find a difference between them, all right? So we're going to divide that into subintervals. Well, why are we dividing it into subintervals? Well, we need a height and a width from each subinterval to be able to calculate the area of the rectangle in that interval. This rectangle approximates the actual area of the subintervals. Well, what do you mean? Well, we are going to divide from A to B into n subintervals. Well, that means I'm going to have a subinterval here, I'm going to have a subinterval here, and I'm going to have a subinterval here, and another one here. And I'm getting sick of drawing these lines, so I'm going to say dot, 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 and I'm going to have some here, and here, and here, and so forth. And I'm going to try to make them equal. They will be in the end, okay? So what we're actually going to end up doing for us, we're going to make all these subintervals along the x-axis so that the distance between each subinterval is the same exact distance so that we can take the width times the height of each rectangle. And that means if I found the area of the rectangle, say in this subinterval, okay, that is going to approximate the actual area in that subinterval. Okay, it might not be perfect, probably won't be perfect, but as I put enough rectangles in there, life is going to be good for it. Okay? Well, we should talk about and name, or we will, and we should talk about and name some quantities in the kth subinterval. What the heck is that, the kth subinterval? Well, K is simply going to be a counting mechanism for us. And bottom line, what it does is it tells us which rectangle we're talking about, which means if K is 1, this is K equals 1 rectangle. This is K equals the second rectangle. This is K equals 3 for the third rectangle. This one's K equals 4 for that rectangle. And then I keep going on. So this last one, this is K equals N for the nth rectangle. And of course, the one just before that would be K to the N minus 1 rectangle just before. That's pretty ugly. To the N minus 1 rectangle. And then this one right there would be the N minus 2 because it would be the second to the N. So it's terminology we need to talk about. What is this K we're talking about? Well, it's simply a counting mechanism that is telling me which interval I'm talking about. Okay? And if I'm talking about the kth interval, well, it depends. I can talk about the kth interval in any which way I wish to do. Okay? So that's where these counting mechanisms come into place. So what I'm going to do here is we are going to move on to the next sheet here. And what I want you to do is recopy your graph right here. And I'm going to hit pause. And I'm going to try to recopy my graph on there so I don't take more time. Okay, so I'm back here. And now remember, this is going to be my K equals 1. This is going to be my K equals 2. This here at the end, that's my K equals N interval as we're moving along there, okay? And some quantities we need to be able to calculate a Riemann sum. And I put in blue there in the kth subinterval or the kth rectangle. Well, what I need to be able to do is I need to be able to identify the kth rectangle. Well, all that is, that could be any rectangle within this whole interval. And I'm going to say, I'm going to dramatize this, and I'm going to say here, I'm going to call this one right here, this is going to be my kth interval. So this big rectangle right here, picture us zooming in, and that is my kth interval. Well, in order to find the area, okay, we need length times width. Well, delta K. Delta K is going to be the width of the kth subinterval, or better known as the kth rectangle. Okay, there's a whole bunch of each rectangle is deemed a subinterval in there. Okay, and so if this is my kth, this right here, this is my delta x sub k. That's the width of the rectangle. Well, within that interval, okay, we get a picket. We need to find a c sub k. And well, what is a c sub k? A c sub k is an x value. Okay, it's an arbitrary x value in the kth subinterval and that's used to calculate the height of the kth rectangle. Okay? And it can be anywhere we want. It can be anywhere we want. So I'm just going to pick one. I say right here, that's going to be my C sub k. Now, when we pick these C sub k's, we're going to be picking nice ones. And what I mean by nice ones, right, left, or middle is what we will be picking. And that'll all make sense here pretty quick. So, and then the last quantity we need is we need to know what f of C sub k is. Well, that is taking my C sub k in plugging it into my function, and what that does is that gives me the height of the kth rectangle. Okay, so I need to know the width of the rectangle. I need to know some random point inside that subinterval so that I can take that x value within that subinterval, plug it into my function so it outputs me a height of that rectangle so I can take the base times the height to get there. Okay? So what that's going to be the area of the kth rectangle. Well, the area of the kth rectangle is going to be taking my f of c sub k, which is my height, times my delta x sub k times my width. Okay, so height times width. That's going to give me the area of that kth rectangle. And what that area is going to do is that area, oddly enough, is going to approximate the area of that subinterval. Okay, so obviously we are going to be doing that quite a few times depending on how many subintervals we will have. Okay, so then the total area on A to B would be the sum of all the rectangles from k equals 1 to k equals n. And remember, k is just my counting interval, or my counting mechanism that tells me which rectangle it's on, and it's written in this form right here. It's written in our sigma or summation notation, which means if I took the height times the width of each rectangle starting from the first rectangle going to the last rectangle, and I added them all together, that is what a Riemann sum does. Okay, this notation right here is telling me to find the area of this rectangle, this rectangle, this rectangle, all of them in between, and adding all those areas up, and then we will have the area beneath the curve approximated, okay? And depending how many rectangles are underneath there is going to dictate how our estimate is going to be. And what we're going to do is we're looking underneath here. Now remember when we touched on this in Algebra 2, because we did do summations in Algebra 2 there, what that is bottom line, remember you put the lower one in for k, and what this does right here, this gave us the area of the first rectangle. Plus, then after k equals 1, because we said k equals 1, then 2, then 3, then 4, all the way down to the nth one, right? So then we next would plug a 2 in there, and then this is the area of the second rectangle. And this is the area of the third rectangle. Plus, this is the area of the last rectangle, the nth rectangle, okay? And as we went through and we did this, okay, to make things convenient for us, this is really important down here on the bottom, okay? To make things convenient, delta x will be the same for all rectangles. Well, hopefully you can look at this and you can see, why would I want delta x in this equation right here? Why would I want delta x in here to be the same number? Well, if you look at it, that delta x, if they're all the same thing, that could be factored out in the end, okay? And to make things even more convenient, c sub k will be at nice spots. And when we're talking nice spots, nice is talking about left, right, or middle. I realistically can pick any point in that subinterval, but I want to pick nice ones, and you'll see why they'll be a lot nicer than any old random thing. It's going to be left, right, or middle. Okay? Then the next thing we need to do is we need to copy that Riemann sum back onto here again. So I'm going to hit. Okay. So as we're saying, nice locations for C, when I'm talking left, right, or middle, this is saying where to place C sub k, which is, this is my x value, and that x value is what's going to be used to find my height. So again, so let's say here is my kth interval. Okay, this is kth rectangle. Okay, and as I'm coming through here with this kth rectangle, okay, what I want to do is if I put, and I guess I should say, here is my delta x sub k for my width. And if I placed on the left side, here, okay, that is going to give me my f of, this is my c sub k, that is f of c sub k is going to give me this rectangle right here, okay? So this would be f of c sub k. That would be my height. Well, if I picked the right endpoint, well, then my c sub k is right here, which means I would be using this rectangle because that c sub k is a little bit less, so that's f of c sub k. Okay, so my height's a little shorter. Hopefully you can see on the green one where we're at on this particular curve is going to be an overestimate, and the orange one is going to be an underestimate. Or, so I'm either going to pick the left endpoint of the interval, the right endpoint of the subinterval, or I'm going to go with the midpoint of the subinterval, which means my c sub k would be taking this one, would be my rectangle, and that would be my f of c sub k. I don't like how I just wrote that. That's okay. And hopefully you can see, ooh, that would be even a better estimate because I got a little under, I got a little over. They're going to kind of, mesh themselves out, but that estimation is going to be somewhere between there. And that's what we mean by nice locations. Now, another little bit of terminology you're going to run into on the AP test. They are going to be circumscribed, rectangles. Well, that would be like my green one. That would be the overestimated one. Or inscribed. And the inscribed one would be like the orange one, which is going to give me an underestimate. Circumscribed, another word for that, would be upper sum, because it's typically overestimating everywhere. Inscribed would be called my lower sum, because that's typically under my curve, giving me an underestimate. Okay, and there's also the midpoint sum. Well, that's this one right here. That would be using the midpoint. So c sub k on my left endpoint in this case would be a circumscribed. And it depends if your function's increasing or decreasing, whether you're circumscribed or inscribed. So knowing a little bit about your functions at the same time is also beneficial. Okay? Some notations or givens that we're going to be doing through here. Well, the givens that we're going to be going through here, just understand here in the beginning, for the beginning of our integration, okay, f of x is always going to be greater than or equal to 0. I shouldn't even put equal to. F of x is going to be greater than 0. That just means my curve is going to be above the x-axis. It's going to be greater than or equal, well, I can say equal to 0 as well. Greater than or equal to 0 on our interval from A to B. Okay? It's always going to be bigger. Now, a couple notations that we're going to be looking at here. Your book kind of does it weird. My old book never did this either. But your book is going to say, find area A to B of f of x. Okay? Now this is really asking you to find the area bounded by f of x, the x-axis, and the vertical line x equals A, and the vertical line x equals B. So basically, this notation right here is saying, here's my function f of x, it's saying find all this area from A to B, saying find all that blue area. Okay, so that's what we're picturing. It's just a little different notation. Different authors do things a little bit differently. And then another notation is we're going to be looking at RAM. Now remember RAM is the rectangular approximation method, and this little sub n tells you how many rectangles you are making within your interval. Okay? And that is, again, it's a rectangular approximation method. And then you will notice many times there's going to be a fourth one in front of that, okay? And it's going to say L for left, R for right, M for middle. So if it's a left RAM, that means you're using your left endpoint of each rectangle to make a rectangle. If it's a R RAM, a right RAM, that just means you're using the right side of that endpoint to make a rectangle to find the area. And if it's a mid RAM or an M RAM, that's saying use the midpoint of that interval to find the area of each rectangle and sum them up. Okay? So let's do an example here, and we're going to do one example 3 different ways, and we are going to be done for the day. So this is your book notation. So this implies right here, this implies f of x equals x squared. So here's my f of x curve. Okay, it also is telling me on the interval from 1 to 5 using, that should be a bracket too, using n equals 4 rectangles. Okay? And as I go through here, what's going to happen is my delta x is going to be found the same way each time. And this is supposed to be, hopefully your notes say 1 and 5 and not 2 and 6. If not, change them to 1 and 5 into 4 equal intervals. That's always going to be b minus a over n, which in this case with a 1 and a 5 is going to be 5 minus 1 over, oh, I had my n there. Sorry, I didn't plug in my n in this case. My n was 4, which is going to give me 4 over 4, which means the width, or delta x of each subinterval, is going to be 1 unit. Okay? And then we're going to place c sub k in each interval to find the height for each rectangle. Now we have options because we can do the left, we can do the right, or we can do the middle. We are going to do all 3 of them here, and you will be asked for all 3 of them on your AP test at different moments in time. Okay? So let's look at this. Let's remember here our f of x function is x squared. We are on the interval. We are going on the interval from 1 to 5 with n equals 4 rectangles. Okay? And this is using a left RAM, so it's a left endpoint. So bottom line, I got to say, well, here's 1, 2, 3, 4, 5. Oh, that's a 4, 2. So that's saying we need the area bounded from there to there, and we are dividing from 1 to 5 into 1, 2, 3, 4 rectangles. So here is my delta x equals 1. Okay? So if I'm finding a left ram, remember, that means we need 4 rectangles. If I have 4 rectangles, I have 4 different rectangle heights. Okay? So my left ram for 4, I know my first, if I'm using the left endpoint in my interval, 1 is going to be the height of my rectangle. So I need c sub 1 is going to equal 1. I know c sub 2 is going to equal 2. C sub 3 is going to equal 3. And c sub 4 is going to equal 4. These are my x endpoints. These are my endpoints that I'm going to be using to make a rectangle. Okay? So, these determine heights of rectangles. Okay, it's important to know. I know the width of all my rectangles. I know the width is delta x is 1. We found that on the previous page. That's my b minus a divided by n. Okay? Which means I know my heights. My heights are going to be f of 1, f of 2, f of 3, and f of 4. Those are going to be my heights. Okay? So I'm finding the area of these rectangles. Hopefully you can look at this and you can say, oh, that's going to be a really crappy estimate. And you're right, it is going to be a crappy estimate, but it's all just a process thing right now that we're going through and understanding what this is doing for us, okay? So I know, in the end, I know my area is going to equal, every time I'm taking my width times my height. My width times my height. So I'm taking my 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4. That's going to give me my area because my width is 1. The height of this rectangle is right there. That's f of 1. That tells me how tall that one is because this is 2 and it hits the curve. That's my f of 2. Okay? So that's where I'm getting my heights from. Well, if you notice here, there is a reason why we are keeping all of our widths the same because they can all be factored out to where it's going to be 1 or my delta x times by f of 1 plus f of 2 plus f of 3 plus f of 4, okay? And I can see that, so I'm just taking the width times the sum of the heights. This right here, this is the sum of the heights. And we're just going to find all those quick. So this is going to equal 1 times, well, f of 1, remember, f of x equals x squared. So when I put 1 into x squared, I get 1 plus 2 squared is 4 plus 3 squared is 9 plus 4 squared is 16. And that's going to be 1 times 10 is 20, I think. No, it's 10 is 20 is 30. And if I take 1 times 30, I get 30 units, okay? So that means my left ram of 4 is 30. Notice I don't have units, I don't have square units on that because I don't know what the units of my graph are. They didn't give me units, so I'm just going to say my left ram of 4 is 30. And then from there, we are going to move on to the next one, and we are going to do a right RAM of 4. Now, I'm not going to go through all of this pain and anguish, guys. Most of the time, we are going to just square down to here, understanding what it is. But for a foundation builder, I'm going to go through them all so you know. Okay, remember, f of x, it's still the same problem, x squared from 1 to 5 with n equals 4, which means 4 rectangles, but now we're using the right endpoint. Ooh, the right endpoint to find the height. Right endpoint for height. That's what a right RAM means. So I got 1, 2, 3, 4, 5. 5, 4, 3, 2, 1. So here's my intervals. And sorry I'm not to scale, I was on the same one. But now if I'm using the right endpoints, okay, now if I'm using the right one, I am looking for these rectangles. And hopefully you're like, woo, that's going to be an ugly estimate as well. And you're right. But notice, delta x still equals 1. But now as I'm coming across here, my right RAM of 4 is going to equal, okay, I have heights of, I'm just going to come over here and I'm going to say heights. My heights are going to come from where? My heights are going to come from f of 2, f of 3, f of 4, and f of 5. And I know my widths, or my delta x equals 1. So if I do this, the area, okay, Riemann sum, the area equals the width times the sum of heights. And that's our shortcut for it. So this area is going to equal 1 times the sum of the heights, that's f of 2 plus f of 3 plus f of 4 plus f of 5, which is going to equal 1 times 4 plus 16 plus, or excuse me, that's 9. 3 squared is 9. 9 plus 4 squared is 16 plus 5 squared is 25, which is going to equal 1 times, what do you get, 20, 45 is 54. So my right RAM of 4 equals 54 this time. Okay? The last part we're going to do, the very last one we're going to do, is we're going to do a mid-RAM. Now everything's still the same. F of x, because this is all going to be the same problem. That's x squared, 1 to 5, n equals 4 rectangles, but now we're using midpoint for height. How do I know that? It's a midpoint, or an MRAM. So I got 1, 2, 3, 4, 5. So here are my rectangles, 1 through 5. The rectangles, if I'm using the midpoint, well now, these are my rectangles. Because it's the midpoint of the interval, that is going to give me that. And hopefully you're like, oh yeah, that's a much better estimate than it was. And I'm not going to use 1.5. I'm going to use 3 halves, 5 halves, 7 halves, and 9 halves, because I'm better squaring fractions than I am squaring decimals. Okay? And the very last thing I'm going to be doing here, we know our width We know that delta x is 1. We know our heights are going to come from f of 3/2, f of 5/2, f of 7/2, and f of 9/2. Those are my heights. And again, my area is going to equal the width times my heights, which is f of 3, that's 9/4, plus 25/4, plus 49/4, plus 81/4, which is 1 times 9, 25, 164/4, which is 164 over 4, which actually equals 41. So my MRAM of 4 is 41. Okay? And we're going to pick up on here tomorrow, on Monday, and then after Monday, you should be able to tackle your homework. Have a good weekend.